Module 1, Lesson 22, Triangle Congruence by Side, Angle, Side. We're going to start off with some vocabulary here. We are going to look at the relationship between a pair of corresponding sides and an included angle, and between a pair of corresponding angles and an included side. Now, included is going to mean between. So let's look at this in our diagram here. This says angle A is included, so there's angle A, between segment BA and segment CA. So you can see that we have a side, segment BA, our angle A, and then side CA. So we have side, included angle, and side as we move around our triangle. Also notice here that angle A is part of both of those segments. It's named in both of those segments. Now over here we have segment BC is included. So let's look at segment BC. There's segment BC right there between angle B and angle C. So in this one we have an angle and then our side and then our second angle. And the side is included between those two angles. And if you notice that B and C here, angle B and C, are both part of naming of that segment. So very important in triangle congruence, order matters. We are going to prove triangle congruence in this lesson by using two sides and an included angle, thus the side angle side postulate. This says that if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then our triangles are going to be congruent. This is convenient because now we don't have to have all parts congruent and all angles and all sides congruent. We can have simply two sides and the included angle, and then we can say our triangles are congruent. So let's look here. We know that if segment AB is congruent to segment DE, and angle A is congruent to angle D, and segment AC is congruent to segment DF, that we can state that our triangles are congruent. And if we look here, now that we've marked it, you can see that we have two sides and an angle that are congruent, and they are two sides and the included angle. The angle is between our sides on both triangles. And again, that is very important. And now this will let us write our congruence statement, stating that the triangles are congruent. And make sure you put in the little congruent symbol here. I've left that out. Oops. You name your triangle, name it in a way that makes it easy to name the second triangle. So this one was named ABC. So we started here at A and went from our angle along side with one congruent mark, and then we went down the side with no congruent marks. And so we would do the same thing on the second triangle. So if we started our angle and go along side 1 and then down along the side with nothing, we get triangle DEF. So triangle ABC is congruent to triangle DEF. Now, it doesn't matter how you name your triangles. I like to find a way that makes sense, that's easy to follow, because how you name the first one determines if it's easy or hard to name the second one. So for this one, I would probably start here at B, go along side 1 to my angle, and then move along side 2. So I would name this triangle BAC and say that is congruent to triangle, and This makes it easy. Downside 1 to my angle, and then downside 2. So that would be EDF. Now it doesn't matter. Both of these congruence statements say exactly the same thing. If you notice, A is still in the same position as D, B is still in the same position as E, and C is still in the same position as F. It doesn't matter as long as all of your corresponding parts match up. A neat little side note here. Do you remember when we were using our compasses to construct congruent segments? We used our compass, a measuring device, to measure the distance from point A to point B. And then we came over onto another line and we measured that distance again, and we said our distance is congruent. Now, if we look at this, why can we say that those two lengths are the same? Well, let's look at our compass. We know that this side is congruent to this side. We've just got two triangles here. And this side is congruent to this side. After all, we are using exactly the same compass, so we know that our legs are the same length. And we used the same angle measure. We left our compass at the same setting, which means we have side, angle, side, and then using CPCTC, corresponding parts of congruent triangles are congruent, we can say that this length is congruent to this length. So that's kind of neat how this all fits together. Let's look at some examples here. Looking at our triangles, can we prove the triangle's congruent? Well, on this first one, I see two congruent sides and a congruent angle, and the angle is included. So yes, we can say that these triangles are congruent by side, angle, side. Now let's look at these two. Well, we have two congruent sides, and I see a congruent pair of angles, but they're not in the right position, are they? The angle is not the included angle, so no on this one. They might be congruent, but we cannot prove it. And this last one, now we have a whole bunch of congruent sides. So we've got our two sides. Can we get an included angle? Well, our good friend vertical angles gives us that. And we could go side 1, angle side 2, and side 1, angle side 2. So yes, we have a pair, we have our sides and our included angles by vertical angles theorem. So yes, we can prove those congruent by side, angle, side. Let's look at some proofs, how to use side, angle, side in proofs. Now looking at our diagram here, I see that we have two congruent sides. These are just given. And right here, can't help myself, that's the reflexive property of congruence. We have a common side. Reflexive property is one of our good friends when it comes to congruent figures. Let's see what else we're given. That's about everything on our diagram. And so we have segment EF and GD. Those are given to us. Ooh, we see that segment EF is parallel to segment GD. Parallel lines means that we have special angle pairs. So I'm going to get out my purple pen and draw my parallel lines. And I see a transversal that cuts across like that. Now, do we have anything that we can use? If you remember, we said that if you have figures and parallel lines, let's look for those alternate interior angles, and those would sit right like that. So we can now say these two angles are going to be congruent, and that's alternate interior angle theorem. So I believe that we can have side, angle, side. Do you see side, angle, side there? So let's look at our define. I forgot a few things on this one too. Apparently didn't do my proofreading as well as I should have here. So we have our given. We have our side that's given and our parallel lines. We have a side by the reflexive property of congruence and an angle by our alternate interior angle theorem, and we think we can use side, angle, side. So when you do your explore, this is what's going to help you set up your proof. You're going to write SAS because that's how we want this to work. So we find our first side. That first side is given to us. And that's just our green side up there. Now our angle, how did we get our angle? Well, we were given parallel lines, which then let us say that our two angles are congruent by alternate interior angle theorem. And then our second side is simply the reflexive property of congruence. So we have all of the parts that we need. And you can see when you mark your diagram, it really makes it obvious what parts you have and how they fit together. So that is just an important part of doing these proofs. So now when we go to write our proof, we simply start out with our side here. Segment EF is congruent to segment GD. That was given. And I forgot the parallel lines on the proof too. So doing our angle takes two steps. We have to have our parallel lines, which are given, and that makes our angles congruent because of alternate interior angle theorem. And then our second side, right here, is the reflexive property of congruence. And then that lets us write our congruence statement. And the reason that we can write that is the side, angle, side postulate. And you can see how we found all the parts in our define, and then we used explore to set up like it's like a rough draft of our proof. It's how we're going to get there, and then in our proof we just put it all together, make sure everything is nice and neat, proper notation, and it comes together very easily. If you do your define explore, proofs will not be as painful as you feel they are. Now another thing that we are asked to do is, I'll move up a little bit here, is to determine what rigid motions can be used to map one figure onto another. So if we redraw here so we can kind of see what's going on, and E, F, D, it's an F, G, and probably the easiest way to do this is to do a 180-degree rotation about the midpoint of segment DF. And you can see that that will map these two congruent sides onto each other and these two congruent angles onto each other if we just spin it around that way. So that would take triangle FGD here and flip it up onto triangle EFD or vice versa. That's the easiest one. Now another way to do this, so we start out with our figure here, E, F, D, G, and we could do a reflection across a line that connects the midpoints of our two vertical sides there. Now, what would that end up with? Well, that's going to give us a figure that tilts this direction. Can you see that? And this would be DG, and this would be EF, because we just flipped it over that line. Now, our figures aren't mapped onto each other, but if we do another reflection, so we're doing composite transformations here, we're going to end up with a figure that goes back this direction. You see that? This will be F, and this will be E. and this will be D, and this will be G. And now the bottom triangle is on the top, and the top triangle is on the bottom. That one's kind of difficult to see. And another option would be we have our top triangle here, and this is point F, and this is point D, and we could do a translation. We could move our bottom triangle along FD, a distance FD, and then it would be down here like this. And then all we would have to do is simply rotate our bottom triangle 180 degrees about point D, and it would flip right up onto it. Now, those are just a couple of options. Many other ways you can do this. Now let's look at using side angle side and CPCTC in a proof. So we look at our figure here, and we are given these two segments. We are given these two segments, and our good friend vertical angle theorem will give us an angle, and that happens to be our included angle. And apparently I didn't edit this entire sheet because fix your angle pairs here. So our define, we're given our two sides. We use vertical angles to get our congruent angles there in the middle, and I see side angle side when I do that. Now we want to prove that angle C and angle E are congruent, and that tells me I know we need to use corresponding parts, CPCTC. So in my Explorer, I write side angle side, match up all of my parts to that, and now I can write my proof. And this is the blue side, which was just given to us. Here is our angle, just vertical angle theorem. The other side was given to us, and then I can write my triangle congruence statement. So I started at the middle angle and went down the green side, and then went this way, and then up the unmarked side. So triangle ABC, that means on the other one I'm going to go down from angle down side 1 to up the unmarked side. This is ADE. You can go any direction you want. And now look, angle C and angle E are in the same position. So I can say angle C is congruent to angle E because corresponding parts of congruent triangles are congruent. Now we could use this on any of the unknown parts. We could say that segment BC is congruent to segment, what would it be? DE, right? Order matters. We just look at our congruence statement and know what it is. We could also use this for angle B is congruent to, that's right, angle D. And all of these fall under the CPCTC. Once you have congruent triangles, then all parts are congruent. So it's kind of nice that we only need 3 of those parts to get all 6. I think we are going to have a lot of fun doing proofs using side angle side and finding unknown parts using CPCTC. I hope you enjoy them.